Alright guys, welcome to Lecture 5 of Machine Organization and Programming. Today I'm going to change the order of things a little bit. I want to go a little bit deeper into pointers. So, quick review to see where we are in the course. During the first week we started to introduce programming in C. We talked about control flow, including conditionals like the if statement, and in some ways the while statement. And then we talked about iteration loops with for loops and while loops and do while loops, and then functions. So the one thing that I've skipped thus far is the switch statement. I'm going to go into pointers today. I'm going to come back to switch later. All right, and the other set of topics we've introduced so far is the data structures, including the four primitives, jar, int, float, and double. We started talking about 1D arrays, and then in specifics, we talk about the character arrays, which is how C will do strings. And then we did the introduction to pointers. Now, I'm going to change the order a little bit because the first assignment involved a number of pointer operations, including passing pointers to functions or passing arrays to functions. So I want to just spend a little bit more time here. And the topics here that I haven't done yet would be the enums and structures. I'm going to come back to these. I tried to line up switch and enum as best I could right here because, in my opinion, they really go well together. So I'm going to address those both at the same time. All right, I'm going to start out with some demo code. You can go to the website. There's a code link on the webpage where you can download all of these examples. I'm going to treat them as starting points and I'm going to modify them. So please follow along. Go grab those right now. And I will meet you back over on a CSL machine in a second. All right. I just got logged in over here into a CSL computer, and these are the files that we're going to be working with today. I'm going to start with array1.c. So let me just open this up and turn the volume down so it doesn't get caught on the microphone. Let's take a look at this. So the first thing I'm going to do is just sort of walk through this code. I'm going to be including standard io.h so I can print stuff out. I've got define max 10. So this is a way to define a compiler variable. It's essentially going to be creating a constant. When you use these compiler defined constants during the preprocessor stage of compilation, anywhere that we see the word max will be replaced with 10. It's just copied and pasted. So as it goes through line by line, it's going to get right here first in line 7, and it'll replace this max with a 10. And then in line 12, it will replace that max with a 10. And in line 16, the third max will be replaced by a 10. So it's just a copy-paste operation that goes through and takes care of all of these variables. You can't change max later. Don't do that. That's not advised. All right, so the next thing we see here is that I'm declaring an array of integers, calling it A, with 10 values in it. And then I've got an integer I that I'm going to be using for my loops. I'm defining it outside of the loops, and that's fine. Then this first loop, all it does is it goes through all of the values in the array from 0 up to max. It'll stop before we get to 10. It's the less than loop. And it's just going to take each of the values and initialize them to 0. And then it goes through from I equals 0 to max, and it's just going to print them out. So here we've got the %d is being substituted with I, so we'll get a 1, 2, 3, 4, 5. And then on the other side, we'll get the value that they've been initialized to, which for all of these should be 0. Okay, I'm going to quit this and compile the code. So GCC, this was array 1, and oops, I need the -o for the output file name. And then this was input code array C -m32 for everything we do in the course, and turn on all the warnings. Okay, looks like it compiled. And there it is, I see array 1 star. So I'm just going to run that. So array 1. And we see that when we go through, we get exactly what we expect. A of 0 is 0. They've all been initialized to 0. So the next thing I want to do is just go back and make one little minor modification. So, yep, pop back in here. So first we initialize the arrays to zeros. I'm just going to take this out. I'm going to move the cursor right there. I'm going to go to block mode with Control V. I'm going to scroll down 4 lines with J to get all of these. When you insert in block mode, I don't think I put this in my Vim tutorial, but it's Shift I. You need the capital version. And then I can type whatever I want. In this case, I'm just going to comment these lines out. The text only appears on the first line until I press Escape. and then the rest of the comments appear for that entire block. Okay, so now what I've done is I'm just going to be printing out these values down here with the print statement, but I've never initialized them. So let's see what happens. I'm going to write quit, compile, and run this. Okay, what we can see here is that I'm still printing out A with all of my indexes, the values of I. But then as we look at this, this is just garbage. So the point here I want to make is that variables are not default initialized. If we were to do something like this in Java, we would find that all of the values would be default initialized to 0. So Java's going to take care of that for us. In C, that's not done. In fact, it makes two different phases go faster. First, the code will compile faster because it doesn't have to do any checking to see if we've initialized the variables. There's no like giving us a warning, nothing. It just lets us do this. And the other thing it does is that as we're running the code, it doesn't have to go through and put in a 0 here as we just declare an empty array. So that's going to go a little bit faster there as well. Okay, I want to go back to the code and make one more change. Let me just grab Vim. Okay, I'm going to go and remove those comments real quick. So Control V to get to block mode, J a couple times, and L to select them all, and then I can just push D to delete them. And that'll take me back into navigation mode. Next thing I want to do is scroll over to this max. So right now we've just been going 0 to max or 0 to 10 and looking at elements that are all in bounds. So I'm going to go and actually increase the range that we're going to print out here. Right, quit. Okay, I'm going to compile this again. And then when I run this, what I see is that the values that I've initialized, 0 to 9 here, are all 0. They worked great. And there was absolutely no warning when I ran the compiler up here. Nothing. When I ran the code, it was perfectly acceptable to see to let me print out values well beyond the bounds of my array. No problem. It did not stop me at all. No warning, no complaining. Java will not let you do this. It's going to give you an error message right when you try and compile this. And a quick warning, don't ever do this. This memory could be allocated to other variables, and by modifying these, we could be writing over them. So yeah, be a little careful about this. This is one of the major sources of bugs in code, is the out of bounds error. All right, the next thing I want to do is jump into array2.c and take a look at this code. All right, again, not a lot here. We're going to be doing some things. We're including standard io.h so we can print stuff. We're going to be defining max of 10 again. Then we have an integer array, my counter variable I for the loops. We're going to initialize the array to be all zeros again. And then the next thing we're going to do is we're going to be printing the address of the very first element of that array. So array A is located at P here is going to be a pointer, so it's going to print it out in hexadecimal of A. And then we're going to be looking at where all of the elements in the array are stored in memory. So we're printing out the address of element A of I. We're printing out a little text to keep us straight. So this will be A of I. So A of 0, A of 1, A of 2, A of 3, so on. And then we're printing out the value. That D is decimal value for A of I over here. All right, so let's just run this and see what it looks like to get started. So do that, and then we need to compile. I'm going to steal my ode compiler line and just replace it with some 2s. There, now it's compiled. I should have array2 star, perfect. And now when I run this, /array2, here's what we're looking at. So check this out. I don't think I did this part before. So the value of A, this is the value that's actually stored in A, not the address of A. This is the data stored in this variable. It's this address, FF849244. So check it out. That address is actually the same as the address of the very first element in the array. So A0 is 0. This is just printing out the data that we have from there on. And then as we look at the rest of these values, I can see this was 4, 4. The next element, element 1, is incremented by 4. That's because the size of an integer is 4 bytes. So check this out. Let me go back. I'm going to go and modify array2.c real quick, and then I'll be right back. Actually, I thought I'd just do this on camera. This is only going to take me a few seconds, and you guys might enjoy watching it. But just a quick review, I'm printing out the address of, and this is the ampersand here is the address of operator. So I'm grabbing the memory address of the elements in the array. So that's what I was printing before. And as we go through this loop, a of I is incremented. So we got a of 0 gives me the address of that. And then a of 1 gives me the address of that variable, and so on. Okay, so next thing I want to do is actually create a character array. Char star, I'm going to call it string. And let me do it this way. I'm going to give it 10 characters. So then in the string, let's put, let's see, A, B, C, D, E, F, G, H, I, J, K, L. Oops, that's probably too many. Hold on a second. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, get rid of those. Now, I know I get 10 characters, but when I create a string, I just want to remind you guys that this is going to be terminated by that null character. Oops, \0. So I need to reserve space for that when I create my string. Okay, next thing I'm going to do is I'm just going to go ahead and grab this loop right here. So I'm going to do Shift-V in command mode, grab these lines, copy them, come down here, and paste them in. Okay, so this is printing out that loop. So my max is 10. I still have 10 right there. I'm not going to change max. Printf, I'm going to grab an address of, oops, str. Yep, and then I'm printing out the value. So in this case, I don't want A, I want str. I is fine, str. So this is going to go through, and it's, yep, so it's going to print the address of str of 0, then str of 1. So it's going to go through each of these characters. So it prints out the address where A is stored, then where B is stored. And this is that address of operator, the ampersand. And then just for some like sanity, I've got the string. This text is just going to let me know which element I'm looking at. So this will be string 0, string 1, string 2, etc. And then I'm printing out the decimal value of whatever's stored there. So when I store characters in a character string like this, I'm going to be getting the ASCII value. I don't remember what they are. Let's go find out what those values are. So I'm going to write and quit, and then make sure I didn't make any mistakes by running the compiler. Looks good, no mistakes. And then we'll just run this code again. So the first thing I was doing was printing out all of those integers. And then starting right here, I'm printing out the ASCII values of the characters A. So right here, the ASCII value of A is 97. It's stored in string 0. And then check this out. Here's my address where it's stored. This is what I wanted to focus on. So the size of a character is only 1 byte. So up here, I was looking at going from 28, 8 is 9, A, B, C. Yep, C, 4 bytes. And then from C, you have D, E, F, and it rolls over to 30. So another 4 bytes right there. But characters are only 1 byte. So, and C takes care of that for us. It's going to store the first one at here 52, and then 53, and then 54, and then 55. So it's going to increment them by 1. So it's going to be as memory efficient as possible when storing whatever data type I want. So if I go with a short, it's going to use 2 bytes for each of these. If I'm using a long int, we looked up last time that size of long is actually only 4 bytes on the CSL machines. So it's going to increment the same way here. 8C, 30, 34, 38. All right, next up, I'd like to take a look at pointers.c. It's the one on the far right there. So let me switch my focus back to CSL machine. So next I want to type vim pointers.c. All right, let's take a look at this code. I just want to emphasize a few more things about pointers, in particular their declaration. So this is review from last time, for the most part, maybe with a little more detail. Okay, so if I read the code here, the first thing I'm doing is declaring 2 integers, a and b, and assigning them values. The next thing we're looking at is the creation of 2 pointers. I'm creating a pointer to a, and so remember that the int followed by a star, anytime I have a data type, like a primitive here, int or char, followed by a star, this is going to be the sign that I'm declaring a pointer. When I use the star later without this prefix of a type, it's going to be the dereferencing operator. So the star is used in two different ways, which can be a little confusing. Now, in this first line here for PA, I'm actually giving my pointer that I've just created an address. So remember, pointers store variable addresses, and the ampersand is the address of operator. So it's being given the address of A. So I don't actually have to assign it an address immediately. I can just declare a pointer, and then later on, somewhere, anywhere I want, I can give it an address at a later point. When I declare this variable, this is just going to have whatever garbage was already in memory from whatever we were doing earlier. So this is going to be completely meaningless, and if we try and access it, it may give us an error message if that memory value is not valid, or it could just give us garbage if it's valid, but there's nothing that's actually been assigned to it that's useful. Or it could potentially very dangerously point to something that I did care about that I don't want to change, another existing variable. All right, but here I am in this line. I am going to assign it to something, so that detail will be taken care of. Next, I'm going to print out the values of A and B. So here, A is going to be printed first, and then I'm going to print a pointer to A. So, and this will be, yep, this is the dereference operator right here. So I'm going to be accessing A. So this dereference means, okay, so A actually holds an address. This is pointer to A, PA holds an address. This says go to that address and use that value instead. Okay? And so I'm printing value A and then the pointer to A. And then I'm printing B and the pointer to B. The followed value, dereference pointer. Okay, right. So this first block prints the values of A and B, two different ways. And then we'll be printing the addresses of A and B two different ways. The first way, using the variables themselves with the address of operator, I'm printing them out as pointers. That's the P there. And so the first one is actually being given the address of A, and then PA is a pointer itself, which already contains an address, P of A. And we'll do that for both A and B. So let me get out of here. We'll compile this. I'm just going to go back up and modify this. Pointers and pointers. Whoops. Typo there. There we go. No error messages. And now I should be able to just run pointers, and it will print out value of A, 1000, just like we expected. We declared that. The dereference pointer, this says follow that address that's stored in the pointer and go get that value, which is 1000. So dereference operator. All right, and then similarly with the address of, I'm printing out the address in memory where A is stored. And check this out. This is the exact same value here. Ends in E1C, ends in E1C. You guys can check the rest of those digits on your own. Same deal with B. E20 and E20. So these are actually next to each other in memory. I declared A, then I declared B. They're just going to be local variables on the stack in the main frame. And so main reserved a bunch of space for them, and they're stored right there. All right, I just want to make one more real quick note here, and I'm just going to do it right at the bottom of this file. I'm going to comment this out in a second, but check this out. When I do star PA, PA is actually equal to, we'll go with that. Remember, PA is, let me put it on the next line. Let's do this. PA is equal to the address of A. So this is kind of like saying star, and then PA, I'm just going to copy and paste. This is like substitution in math. The ampersand A. So that's really what we've got here. Now, because of precedence, oops, didn't mean to put that in. I'm going to throw some parentheses in and just write this like this. Okay, so this is exactly what's happening. I'm dereferencing, and then the value of PA is actually the address of A. So this star and the ampersand are like inverse operations. They're just going to cancel each other out. And when I type this, star PA, anywhere in the code, it really means A. All right, next up, I want to take a look at null.c and introduce a new concept here. So let's switch focus back to this screen. So we'll pull up null.c. And check this out. We're going to be printing stuff, so I've included standard io.h, normal stuff. And the first thing I'm doing here is I'm declaring a pointer. Now, normally, what I would have is just something like this thus far, and just declare pointer and just let it be whatever address is in memory. Now, it's generally not good practice to declare pointers and not have them point to something. So C provides this special operator, special symbol called null. And this is essentially just going to assign a pointer to a particular address where we can recognize that it's not been assigned to a real variable yet. So in this case, it's going to give us a compiler error message. And so you let me walk through the rest of the code. I'm declaring a pointer. I'm assigning to this special address. Then I'm trying to dereference the pointer and assign whatever is in that address to be 10. Now this is not accessible by the operating system will actually stop me from doing that and throw an error. So let's go take a look at that. So compile. And then we'll run this. And the error we get is actually called the segmentation fault. So essentially the way this works is that a built-in compiler define is included, something like this. It's just going to define null to 0. And the special memory address 0 is reserved by the operating system. No one can access it. So if we actually try and access memory address 0, our program will crash. And we'll talk about why that error was called a segmentation fault during the last third of this course. So one of the reasons we would ever be interested in doing this is because if you remember how if statements work, if I have all of these statements or expressions get evaluated into a number. Basically C is just going to do some math and simplify them. But what I can do is I can say if P, and if P has been assigned to null, null is 0, this is essentially saying if 0. And remember, 0 represents false, and anything else, which means any other memory address, will be true. So I can do this to check and see if so I can check and see if P is valid. And then I can do whatever I need to with P. And if P has not been assigned yet, then I will know that P has not been assigned and I can take care of that situation. Alright guys, so the next thing I want to take a look at is this connection between arrays and pointers. They have so many things in common and really only one difference that I'll highlight at the end. So I'm going to pull up arrays and pointers 1. We'll take a look at this. This is the file as it is right now is almost the complete code that I'll be generating at the end. So this is what you guys have access to online when you download it. I'm going to go ahead and take out all of the pointer stuff and talk about arrays and then build in the pointer material. And let me just go through it from the top. So same stuff as before. Standard io.h. I'm defining the max for my array size. Here, this is the first file I've used today that has a function in it. So it's a function called print array. All this is going to do is take an array as input, and it doesn't do anything. It's not going to return a value, but inside the function, which is defined at the bottom of the file, it just prints out the array. So C, as it goes through the code to compile things, reads it one line at a time. So include, copies and paste that file in, define. It's going to remember that anywhere I see max, I need to replace it with a 10. This is a function prototype or a function declaration. All it says is that when I actually get to a function called print array, there's one right here in line 18, I know that it doesn't need to return anything, so I can't assign this a value, and that the only parameter it takes is an array. So this is an array of size max. There it is, passing in the array. The function definition is actually found at the bottom of the file. It's pretty simple. Just iterate through the array and print array with the index, so array 0, array 1, a2, just like we've seen in the other files, and then the value of that array. And in fact, if I wanted to, here, let me just go to visual line mode. We'll grab all these lines, I'm going to copy them. One sec. Go to visual alignment. I'm going to delete them. That's the same as cut, so I just push D to do that. I'm going to go back up to the top. If I wanted to, and paste them in right here, I can actually move the entire definition up to the top. And if C sees the first line here, line 5, it knows it's a prototype and it should expect the function declaration later. This ends in a semicolon. Or I can put the actual definition right here, and this should also work just fine. So I need one or the other. I'm going to leave it in the original file as the prototype at the top and the code at the bottom. That is a more common way to do things. It's a little more organized. And then we'll keep, it keeps main closer to the top. All right, so the next thing I'm going to do is let's take a look at the actual code itself. I'm going to get rid of all the lines dealing with the pointers to start out with. So first thing we'll do, we'll fill in some values into the array. It's going to have values 1, 2, 3, 4, 5, etc. up through max, which will be 9 in this case because it's a less than operator. Then we'll print it out. Then let's see here. Then we'll go ahead and we'll modify the array using index notation. We'll print it out again, and then I'm going to start getting rid of this pointer stuff. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 DD moves all those lines, and that should be enough to get started. So that looks pretty good to me. Let me save and quit, and then we're going to compile to make sure I didn't mess anything up. So GCC arrays, -o, output, arrays and pointers 1, arrays and pointers 1.c -m32 all the warnings. Okay, looks like I didn't break anything. So now I should have a file called arrays and pointers 1 that I can run. And exactly what I just said. So the first thing it's going to do is go through and initialize all the values of the array. And then we're going to modify the array using array index notation. Let me go back and just point out that exactly what that is, what I'm referring to here. So this is what I mean when I say array index notation. It's the standard way we do things in Java. It's the normal way we do things in C, with just the brackets and an index. Now, pointers are extremely powerful, and we have more than one way to use them. Actually, before I do that, let me go to PowerPoint and actually draw a picture of exactly what we've got right here. Hold on one sec. All right, I've gone back and grabbed my memory model slide. A couple of little notes. Because these are integers, I've relabeled these, so offset by 4. So address 8, address C, address 10, address 14, 18. So 4 bytes for each integer. And I've just, I haven't written out every single byte that's completely zeros. I just put in the decimal version, so 0, 1 through 9. So I'm not writing them in binary anymore, just for a little more simplicity. So, and I've also just stuck them in. I picked memory location 0, 8 to start. C is going to be completely in charge of deciding where to put it in memory for now. And yep, we've initialized all the values 0 through 9. Now, as we go through that next loop and we start updating the, before I move on, I've got one more thing here. The variable array is actually a pointer. And what this contains is the address of the very first element. So when I declare an array like this, not only does it reserve memory for all 10 elements, it also reserves memory to store the location of that array. So just want to point this out. So somewhere in memory, and I've stuck it in address 24, I've got an array variable that contains the address of the first element of this array. So this would be array 0. Okay, so then as I go through, when I actually go through and modify that, so I'm just assigning them 0, 2, 4, 6, 8, etc. in the second loop, what I'm looking at here is array of I, and then internally inside of C, this is what it translates this command to with the bracket notation. It's going to say take the starting address of A plus however many elements I want to offset by, times the size of an integer, so it knows how far down to go. So let me click again. So for example, capitalize those. I hate the way PowerPoint does that. All right, I'll go back and fix it in a second so that the slides are right online. So for example, if I'm looking at array element 2, what this is going to do is say take the starting address of the array and add, so I is 2, the size of an integer is 4. C already knows that the array is an array of integers. The compiler took care of that for us when we did the variable declaration. C is a strongly typed language. I'm required to put that in. All right, so then the address of the word array, the variable array, is 8. And so it substitutes that. It's going to add 8 to that. In hexadecimal, that's 2 places down, or 1 0. So yeah, so when I use array2 like this, internally it does a bunch of math to figure out the exact address, and then it's going to dereference that address, and all this is just done implicitly. So this is what's happening under the hood inside every time I type array2. All right, so that's what's happening under the hood. If I want to actually use this in code, one of the things that's going to be a little different is I don't need to take care of the multiplication by the size of the integer. C already knows it's an array of integers, so I can just get away with typing array plus 2 and then dereference it. And parentheses are there because the dereference operator has a really high precedence. Here we go. Because C already knows that it's an array of integers, it's going to take care of that multiplication by 4 bytes. And if I'm using a different compiler later in the future, or a different set of hardware that has a different size for integer, because those sizes are not guaranteed, I still want my code to run. I don't want to have to go back and change everywhere just because I'm running on a different system. Okay, next thing I want to do is actually demonstrate using that. So I'm going to go up here and grab this code. So line-based visual mode, we'll grab this, I'm going to copy and paste it down here. And then switch to insert mode, modify the array using, let's see, what should we call this? Pointer notation. Let's call it array pointer. So I haven't technically made a pointer yet. Okay, so the array is modified using array pointer style notation. Okay, again, I'm going to go through and iterate through all of the elements in the array. But now instead of accessing them with this array index notation, I'm going to take this out and I'm going to just add I to them. Now, if I do this, I need to dereference that because this array is a pointer. I'm just adding some an integer to it. In fact, it'll be the integer times the offset because it knows that it's an integer array. And then I need to put the dereference operator, so I actually go get the value stored at that address, not the actual address itself. And then let's go with I times 3 just so we can see that it's actually changed. And then we'll print the array out again. So write and save, compile, no errors, awesome. I'm on a roll today. I've only made like one mistake. All right, then we'll just run this. Okay, so we can see that we are actually able to modify the array. So when my print function is still using the index notation as my clue to myself, my little prompt. And then it's actually replaced all the variables in the array with I times 3. So 0, 3, 6, 9. All right, now I'd like to start introducing the idea of pointer array equivalence. So let me, oops, focus is back on my recording software. There we go. Plotter P pointer. Pointer array equivalence. Come on, Mike. There we go. Just want to make a little space. So here's what I want to do. I've got my array. It's declared on line 14 at the top of the screen. You can see it there. Int array max. Now what I'd like to do is declare a pointer to that same spot. So I'm just going to call this P array, pointer to an array. And I've got two options here for how I can do this. I can say give it the address of array element 0. So remember, this array element 0 is actually going to be dereferenced automatically for us and go to that memory location and use that value if I were to do that. By throwing the address of operator in front of that, it will take care of the getting the address of that. And now my pointer P array will point to the very first element in the array. All right, another way to do this is to just remember that the array itself is already a pointer. If you remember that memory model, I had my P array with the address of the first element in the array. And P array is just going to be get a copy of that value. All right, I'm going to jump back and put this into the memory model in PowerPoint. And I forgot to draw the arrows last time. One sec. All right, I put the arrow in just to remind myself that this array stored at some location, doesn't matter where, has the value of the address of the very first element of the array. So this is what's important, that one right here. And this, maybe even a better place to put this would have been right here, that end of the arrow. It points to the very first element in the array. Now, when I declare a pointer, pArray, and give that the address of, or give it an array, which is an address, it just makes a copy of what's in this memory location right here. So it's going to copy 0x08, right there, 0x08. And what that's going to mean is that this pArray also points to the very same memory location. So basically these are aliases of each other, and I can use them almost identically. All right, I'm going to go demo that, and then we'll talk about the one difference between the two of them. All right, so I've just gone ahead and declared pointer and assigned it the value of array. I only need one of these. If I have both, I'll be redeclaring a variable. That'd be an error, so I put some comment marks right there. And then I'm just printing out the array, and as a pointer, so this is going to give me the address in hexadecimal of array to show you that it is a pointer, and also printing out the value of pArray. So let me write in quit, and then we'll compile and run this. There it is. And now we can see that the array and the pointer both contain the exact same memory address. All right, next up, then go back to here. I want to go ahead and use the pointer to modify the array. So right now, I'm going to go up here to line 31. I'm going to grab all these lines, copy them, and down to the bottom, we'll paste them in. And then I'm going to, instead of using, I'm going to modify the array using actual pointer notation. Array is modified using pointer notation. Oops, got an extra space there and there. All right, cool. So I'm going to just iterate through this. And now instead of using the array, I can just use pArray. And then that will print out the exact same thing. Oh wait, hold on. I don't want to print the exact same thing. I want to know that it's actually different. I'm going to change this to 4 also. So replace, oops, there's 4. Save it. Now compile. And run it. So here we can say I've now used the array modified using pointer notation, and I changed that to 4, so 0, 4, 8. And it works exactly the same way. I'm still passing array to the print function statement. Right here. Oops. Passing the array to the print function right there, and it printed just fine. In fact, if I wanted to, I can insert a p right there and print using the pointer to the array. Let me quit this. We'll compile, and we'll run it again, and it prints the exact same way. I'd also like to demonstrate that, let me go back here, I can modify the array using a pointer with array index notation. So let me grab another copy of this. Let's see here. Command mode, Shift V, grab those lines, paste those lines. There we go. Using pointer notation with array access. Let's see here. Y for W. Pointer with, paste those in. Pointer notation with array access. Looks good. All right. So then, instead of using this notation right here, I'm going to go ahead and switch this back to the bracket. And we'll just change this to a 5, and we'll print out the array again. And now 0, 5, 10 totally works. All right. Now the major difference between arrays and pointers is that arrays are essentially constant pointers. I cannot change the value. So if I want to do something like here, array equals array plus 1. If I just want to move to the next element, this is not going to work because the array was declared up here on line 14 as this style of array, actually declared as a regular C array, which is essentially a constant pointer to those memory locations. So if it were constant, I just got a label here. That means this value cannot be changed. And this line right here will not work. The compiler will throw an error. So let me just demonstrate that. Yep, here's the error. Assignment to expression with array type. That equals not allowed because it's constant. So next, if I go back in and instead change this, I can actually do the same thing with the P array. Pointers are not constant, and I can definitely change it. So if I were to do this, and let me jump back to PowerPoint in editing mode, this is essentially going to add 4 to this value right here. So from 0, 8, it's now going to go to 0, C, and this arrow right here is now going to point at the next element down. And so if I print out that value, I should get a 1. So let's go ahead and do that. So printf array. Actually, I want to do. Let's print the address, and so that'll be a percent %p, and then we'll throw in a tab, and then we'll print out the dereferenced P array %. In this case, it's an integer, so we need %d. New line, finish up the, and then we want P array and dereferenced P array. And I need a quotation mark right here. That looks good. Semicolon at the end of the line. All right, let's try this out. That's the wrong command. There it is, compile and run. Okay, so we can see here that, oh, that's right, I modified the array. I was expecting a 1 when I did this, but I've modified the array, so when I print that value out, I'm no longer looking at the 0, but I've adjusted that pointer to point to the second element. So array 1 is now actually the value 5. The other thing I can see is that P array was stored at this memory location after I've modified it, so 0, 8, but when it was first declared, I printed that up here. It was actually stored at the 0, 4 address. Alright, I just have one topic left that I want to cover in this video. So I'm going to jump into arrays and pointers 2. This is the next file we'll be looking at. Switch the focus back to CSL. There we go. So this file is very similar to the one we were just looking at. It's sort of a stripped down version that's only got just a couple features. So I've got my print array function right here, declaration. I've got main. I'm declaring an array, counter variable. All I'm doing is going to fill it in with 1, 2, 3, 4, 5, and then printing it out. So what I want to point out, though, is that I can pass a pointer to an array instead of the array brackets as a parameter. So in this case, and in fact this works, they're equivalent as far as C is concerned. So I can declare it with an A brackets up here, and then I can give it a pointer down here. These are exactly the same thing. So let me just run this code and demonstrate that it doesn't crash when we do this. So let's see, you got my compile line. This is function 2. Compiles just fine with no errors. And then we'll go ahead and we'll run this. Whoops, oops, oops, oh dear. And that's what I want. Okay. So I was just looking at the binary code for the compiled version. So yeah, it works with no trouble. I'm printing out the array. I'm printing out those initialized values. Let me jump into PowerPoint and just real quick go through what's really happening here. All right, so when we begin executing a program, I'm looking at, so this is not the memory model that I had in blue. This is the call stack diagram. So when I begin executing a program, it's going to reserve some memory. And the very first stack frame that gets placed is for main. Inside of main, we're going to have the local parameters This would be the command line arguments. It'll also reserve space for any local variables. In the program I was just running, the only local variable, I had several local variables, but the one I care about right now is the array. And then it's going to store some stuff, return value information that the operating system will need when main is done executing. Then, when I called print array, that function, it will add a second stack frame, just right on top of the stack for print array, and that's going to store parameters. In this case, print array took one parameter that was a pointer to an array. It's also going to reserve space for local variables like I that we iterated through for the printing out of all the elements. But what I want to point out here is that this A is actually referring to the exact same location as this array. They're different. They're not the same variable. All of the variables inside a function are going to be local variables to that function. And everything that C passes to a function is passed by value. So it takes the value in this array, which is an address, and it passes that address up here to array. So this pointer also now refers to an address. It basically gives us access to the same data. I can essentially refer to data that's available only in the main function in this frame through this copy of the variable. So it kind of looks like a call by reference, but what's really being passed is the address of the memory. All right, guys, this is going to do it for me today. Please remember that the first quiz is out. It's available beginning at 8 a.m. this morning and will be available until Wednesday at 8 a.m. Our first homework assignment is due on Thursday at midnight. I hope this video will help you guys understand what's going on with the passing the arrays to those functions in that assignment. And if you have any questions about this lecture or the homework, be sure to go ahead and put them on Piazza for us. All right, have a great day.